So what we're doing is we're moving into 5.3. Right? But we're not going too deep into this section. What we're talking about today is just verifying solutions. If we delve any farther into it, which I don't think we're gonna, I think I'm gonna move it along into the next section after this. We would just be solving for them just like we would any other thing where we're solving for a variable, right? Where you're isolating a variable to one side to see what it equals. But in this specific case, we're just verifying solutions. But before we can do that, we need a little refresher on our friend, the unit circle. The unit circle is my favorite thing in math. I'm doing pretty good. I was going to say, even if I'm bad at drawing it, but so far, I'm doing pretty darn good with it, right? So if you remember correctly, if we were dividing from here to here, like if we were going halfway around the circle, it would be going from 0 all the way to pi, right? And if I divided this from 0 to pi into 6 separate pieces, right, 30-degree increments, these are not necessarily the best 30-degree increments, but it would mean that I'm dividing each quarter into 3 pieces, right? Because we're saying that technically these are 6 even pieces that we're dividing it into. So this would be 1/6 of pi, right? So it would be pi over 6. This one right here would be 2/6 of pi, right? And if we looked at that, if we reduced that fraction, it would be pi over 3, right? This one will be 3 pi over 6, which is just pi over 2. This would be 4 pi over 6, and if we reduced that fraction, it would be 2 pi over 3, and so forth, right? We can go all the way around. This would be 5 pi over 6, which doesn't reduce. This would be 6 pi over 6, which is just pi. 7 pi over 6, 8 pi over 6, right? And we're just counting our way around, right? 4 pi over 3, 9 pi over 6, right? And when we reduce this, we get 3 pi over 2, 10 pi over 6. And we're just counting pi over 6 all the way around. How many of them are there? 5 pi over 3, 11 pi over 6, and 12 pi over 6 just equals 2 pi, right? And we could do that with 45-degree angles as well, right? And if you remember, each of these have a point value, right? This one would be radical 3 over 2 and 1/2. And this one would be 1/2 and radical 3 over 2, right? This one right here, our x value is 0, but our y value is 1. And then if we go here, it's this one, only we're going to have different values, right? We're going to have a negative 1/2, positive 3 over 2. And we could do this all the way around, right? This one's going to be the same as this one, but our x value is going to be negative, right? The only thing that's going to change the rest of the way around on these is the sign, right? Everything on this one is negative. Everything on this one, the x's are positive and the y's are negative, but those values that we attribute to them stay the same, right? If you look at these signs, if you remember, our x values are cosine, right? And our y values are sine. And I know this is all just review, but it's been a while since we looked at it, right? Do you have to memorize how to get this? No. Go on Google, look up unit circle. Go to one of the old sheets. Maybe I'll post it in PowerSchool, one of the old sheets that we have that have all that on it already. But what I really want you to get at is that these all have values, right? If I say cosine of pi over 6, it's going to be whatever that x value is at pi over 6, right? Cosine of pi over 6 equals radical 3 over 2, right? Because that's what the x value is at pi over 6. If I were to say, what is cosine of 5 pi over 6? You would come over here to where 5 pi over 6 is, and you would give me the x value. If I were asking you what is sine of 2 pi over 3, it would be the y value, right, at 2 pi over 3, which is radical 3 over 2. Does that make some sense? Okay. Cool, because that's going to make the rest of this easier, because we only have a couple of problems to go over. I'm going to show you how to do. I just took sample problems from the little homework section that I'm giving you, because I think that's the best way to see how to work anything. But what we're looking at is just plugging things in and verifying if they're true. So if I have, for example, tangent of x minus radical 3 equals 0, and I need to verify that, I need to work through this problem and figure out if this is true, right? Well, tangent of x, we've got to give us our x values first, at pi over 3, and then we'll do b over here, which is x equals 4 pi over 3. So if I have to verify if it's true when x equals pi over 3, all I'm doing is plugging that in, right? I have tangent of pi over 3, right? I'm trading that x for pi over 3, and I need to find out if this is a true statement. So I have to figure out what tangent is at pi over 3. Well, if you remember correctly, tangent equals sine over cosine, right? So for us, that is going to be y over x. So I'm going to go to pi over 3, which is right here. And I'm going to go radical 3 over 2 over 1/2. Right? Because I have to figure out what that tangent is when we have pi over 3. So to figure this out, we're going to go radical 3 over 2 times the reciprocal, right, which is 2 over 1, which gives me 2 rad 3 over 2. And these cancel, and we just get radical 3. So now when we look at this, we're saying that radical 3 minus radical 3 equals 0, which means that 0 equals 0, so it's true. If we look at part B, we're saying the same thing, right? We're asking the same question. We've got tangent of x, but now we're saying that x equals 4 pi over 3 minus radical 3 equals 0, right? So we have to figure out what we get at 4 pi over 3. And if we come out here to 4 pi over 3, I did not write it out, but we're going to get the same numbers, correct? We're still going to have 1/2 right? And radical 3 over 2, the difference is they're both going to be negative, right? Because everything in this quadrant is negative. Our x is negative and our y is negative there. Do you kind of see that? So I can solve this one out for, ooh, maybe I can. I lost my mouse there. I could solve this one out for you, but really it's the same thing we did here, right? Except for we're looking at this, it'd be negative over negative, which gives us a positive, right? So we wind up with the same solution. Did you see what I did, right? If I have negative 3 halves over 1/2, when I multiply these, they're just negative times negative, and that gives us a positive. And so we wind up with still radical 3 minus radical 3 equals 0. The next example I did, I got at a tangent. Like the next problem was either tangent again or cotangent. And I'm like, I don't want to figure it out again. So I picked one that had sine and that worked a little differently. So our next example, we'll do in purple. So if I have 2 sine squared x minus sine x minus 1 equals 0, and I have to verify this for A, which is x equals pi over 2, and B, which is x equals 7 pi over 6. Same thing, what are we doing? We're just plugging in, right? Here I have 2 sine squared x. Well, that's just 2 times sine squared pi over 2 minus sine of pi over 2 minus 1 equals 0. And when we go to figure that out, we have to go, well, we're going to have 2 times what is sine of pi over 2. And if you think about that with the circle, right? Pi over, ooh, I like it when it does that. Pi over 2 is right here, right? That is our 90-degree angle. So what we're saying is that x is 0 and y is 1, right? But when we're dealing with sine, we need to know what the y is, right? And in this case, the y is just 1. So we've got 1 squared minus sine of pi over 2, which is just 1, minus another 1, which equals 0. If I square 1, it's still 1, so I wind up with 2 minus 1 equals 0, which is the same as saying 0 equals 0, and so we know that's true. Did you feel that, Avery? 7 pi over 6. Well, what do we get with 7 pi over 6? Let's come up here, look at our unit circle. 7 pi over 6 is right here. It's going to be negative 3 halves, negative 1/2, right? So our sign that we're dealing with is negative 1/2, right? Because that's our y. And so that's what we're just going to plug in for each of these, right? If I'm doing 2 sine squared x minus sine of x minus 1 equals 0, what we're plugging in for sine squared of x is 1/2. So we've got 2 times 1/2 squared minus 1/2 minus 1 equals 0. And now we just have to do the math on that and prove it, right? So if I look at 1/2 and I square it, I've got 2 times 1/4 minus 1/2 minus 1. If I multiply this times 2, I have 2/4 minus 1/2 minus 1. Keep my equal 0. 2/4 is just 1/2, right? feel like I did something wrong here. Oh, this is minus 1/2, right? So this would be plus. That's where I screwed up. So this becomes 1/2 plus 1/2 minus 1 equals 0, which gives me 1 minus 1. So these check out, right? So all you guys are doing is plugging it in, but you have to go and figure out what those values are. And that is all we're covering today, right? I'm giving you 4 problems. They have an A, B. They're all like this. I haven't put them in PowerSchool yet, but they are page 370. I'll have them up in PowerSchool next period. I would have had them up sooner than that, but I haven't had a chance to go and save the PDF yet. And you're just doing numbers 6, 7, 8, and 10. But I want to see you work all those problems out. But they're really not that hard if you look up a unit circle when you're doing it. I mean, don't try and guess at the values. You don't have to go and figure out the values. All you have to do is look at a unit circle, and it'll give them to you. Any questions on that?